So, today we will discuss various types of discontinuities, and then we will see the relation between continuity and compactness, continuity and compactness. Okay. So, let us see. First, we know a function f x is said to be continuous at a point x naught belonging to the domain say E, which is subset of say x d, if and only if limit of this function f x when x approaches to x naught exists and equal to the value of the function at a point x naught. Now, if this condition, when we are saying limit of f x tends to x naught equal to f x naught, it means the function must have a limit when x approaches to x naught, that is the left hand limit, right hand limit, both exist, they are equal, and the value of the function at the point x naught must coincide the value of the limit f x when x approaches to x naught. Then only the function will be said to be a continuous function. If any one of the condition fails, that is, if either the limit does not exist, that is the left hand limit of this function when x approaches to x naught from the left hand side different from limit of the function f x when x tends to x naught from positive side, then we say the limit does not exist at that point, or maybe if the limit comes out to be infinity for that. In that case, one or limit exists, but is different from the value of the function f x naught. So, when the limit does not exist, left hand right hand limit does not exist, then also the function will not be continuous, or if the limit exists, but its value is different from f x naught, then also the point x naught will be said to be continuous. Or it may sometime happen the limit of this function f x when x tends to x naught and y tends to y naught, both does not go to mean left hand limit also does not exist, right hand also does not exist, then also we say the point x naught is a point of discontinuity. So, if this case is there, then x equal to x naught will be considered as the point of discontinuity for the function f x. So, obviously, the point of discontinuity depends on the cases whether limit exists, but different from x naught, then we name this point of discontinuity to some like a removable discontinuity. When the limit does not exist, then we give some other name to the discontinuity, or when the limit does not exist, left hand and right hand limit does not exist, we also give some other name, or sometimes the limit tends to infinity, then also we give sometimes different name. So, according to the situation, the type of discontinuities are characterized. So, first is, let us see types of discontinuity. First is removable discontinuity. Okay. So, removable discontinuity, if the function f x is said to have removable discontinuity, at a point say x equal to x naught, at a point x equal to x naught in the domain, if the functional limit, if limit of f x when x tends to x naught from negative side equal to the limit of this function f x when x tends to x naught from the positive side, they exist and both are equal, means left hand limit is the same as the right hand limit. So, limit exists, that is the limit exists. And second one is the functional value f of x naught also defined, is also defined, but the third is the limit that is limit exists. Third is limit of this function f x when x tends to x naught is not equal to the value of the function at a point x naught. Then we say x naught is a point of discontinuity and we call it as a removable discontinuity. Why removable discontinuity? Because we can redefine the function again, so that it can be, the new function will be continuous, because the reason is this function can be redefined in such a way so that the new function becomes continuous. That is, if we define capital F x as our small f x when x is different from x naught and equal to the limit of the function f x when x tends to x naught, then the new function f x so obtained will be a continuous function. Then f will be continuous. F x has x naught as a continuous point. So, this function f in this where the x naught was a discontinuous point can be converted to a continuous point by simply removing or redefining the function. For example, if suppose we take the function f x is defined as say x for 0 less than equal to x less than half equal to 0 for x is equal to half and equal to say 1 minus x for x lying between half, open at half, close at 1. So, over the interval 0 1 we are defining the function. So, the function is of this type. This is 0. So, between 0 to half the function is a y equal to f x. So, it will be something like this. This is half, this is half, here is say half. Okay. And then at the point half it is coming to be 0. So, basically this half, this point is excluded here, we are not touching half here, it is coming down, is it not? And then from this point when x is not half, just near to half, it is start from here. So, we are getting this thing and then at the point 1 it is coming to be 0, this is 1. So, what we see here, except at the point 1 the function is very smooth function. Okay. So, here if we look the limit of this function f x when x approaches to half minus, then this is the same as the limit of the function f half minus h, h tends to 0. From the left hand side you are approaching, from here you are approaching. So, take the point x is a half minus h. So, this is the point half minus h. Okay. So, consider this. Now, when the point is lying between 0 and half, the function is defined as x. So, this is equal to half minus h and then limit of this h tends to 0, which comes out to be half. So, from the left hand side, the value of this limit is coming to be half. Now, from the right hand side, if you look, limit f x when x tends to half plus, then this is the same as to write limit h tends to 0, have f of half plus h, choose the point here which is half plus h and then approach about this side. Okay. So, when the point is lying between half and 1, this interval is taken in consideration where the function is defined like 1 minus x. So, 1 minus this and then take the limit as h tends to 0. So, this comes out to be half minus h and then h tends to 0, which is equal to half. So, right hand limit and left hand limit both are coming to be same as half. So, limit exists. Therefore, limit exists, limit of this function when x tends to say half exist. Okay. And equal to and equal to half. But the value of the function at the point half is 0, which is different from the value of the function at a point half, sorry, at the point half, because the value at the point half is given to be 0. Here we are limit value is coming to be half. It means this function has such a function where the limit exists, but the value of the function at that point is different from the limit. So, half becomes the point of removable discontinuity. So, x equal to half is the point is the removable discontinuity for this function f x. Okay. So, if we redefine the function instead of 0, if I redefine the function here, if I redefine the function here with value at x equal to half, then our function becomes continuous. So, that is why removable. Now, take another example, suppose another one. 2. Let us define the function f x as f x equal to limit of this as n tends to infinity cos to the power n pi x, where x lying pi x, okay, where the x lies between minus 1 and 1. Okay. It is not covering end points, open interval minus 1 to 1. Now, if we look the function cosine of this function, cosine pi x, when x lying between minus 1 to 1, the function phi pi x has the graph like this, minus 1 to 1. When x is 0, cosine 0 is 1. Okay. So, when x is half, pi by 2, the cos 90 is 0. Similarly, minus pi by 2, it is 0. So, it will be something like this. Okay, something like this. And when x equal to minus 1, but it is not touching minus 1, is not touching. In fact, this point is not attained. Okay. Similarly, this point is not attained. So, but when it is minus 1 and plus 1, the value is coming to be minus 1. So, this is the graph of this function x and this y x. So, value of this is 1. Okay. X y is 1 0 1 in this is the 0 1 point, and here this point is say minus 1, here this point is 0 minus 1. So, cosine of this thing for this function, clearly cosine of pi x always lies between minus 1 2 plus 1 except for x equal to 0 where the value is cosine 0 is 1. So, when x is different from 0, the value is always minus 1 2 plus 1, that is mod of cosine x will be less than 1 and there. So, this shows that mod of cosine pi x will remain less than 1 for all x belonging to the interval minus 1 to 1 minus singleton set 0. This is our goal. Hence, limit of this function cosine pi x to the power n when n tends to infinity, this limit will be 0 because this is always be less than 1. So, n is infinity, it goes to 0 for all x belongs to minus 1 to 1 minus singleton set 0 and equal to 1 for x equal to 0. So, what throughout this function attains the value 0. Okay, function is very smooth function, it is continuous except at the point 0, because what happened this, when you take the left hand limit of this function f x is cosine n to the power pi x, limit of this is f x. So, when you take the f x means 0 minus point, the left hand side point, it means the limit of this thing, limit of cos n pi 0 minus h, just you take the 0 minus h and then here. So, this number will be less than 1 mod of this. So, this will be 0. When you go from the outside, the limit of this the function limit of this function as n tends to infinity, cos of n pi 0 plus h is also 0, that is f of 0 plus, but the value is entirely different from f of 0 because f of 0 is 1. Therefore, 0 their function 0 x equal to 0 is the point of discontinuity and it is a removable discontinuity. That can be easily seen for them, okay, at x equal to 0. So, this is the first kind of discontinuity, that is removed. The second type of discontinuity, we call it as a discontinuity of first kind. Discontinuity of first kind, or sometimes we also call the ordinary discontinuity or ordinary discontinuity ordinary discontinuity at this point. Okay. So, what we say is, if the limit exists, both the left hand and right limit exist, but they are different. If a function f x is said to have a discontinuity of first kind at the point x equal to x naught, if limit of this f x when x tends to x naught plus and limit of this f x when x tends to x naught minus, that is right hand limit, and limit exist, both the limit exist, but they are different from have different values, both exist, but they are different. We are different. They are different means they are not equal. That is, left hand limit f x when x tends to x naught plus is different from limit of this function f x when x tends to x naught minus. So, both are different. Then x naught will be said to be a discontinuity of first kind. Okay. Now, since we are in the continuity, we also test the value of the function at a point x naught. So, suppose the value of the function at a point x naught, which is well defined, and if it coincide with one of the either left hand limit or right hand limit, then we further classify it. If the value of the function f x naught coincide with the right hand limit of this, then we say, so if further if the left hand limit of the function f x when x tends to x naught minus coincide with the f x naught, while the right hand limit of this function f x when x tends to x naught plus exists, but different from the value of the function at f x naught, then point x naught, then point x naught is said to be ordinary discontinuity, ordinary or discontinuity of the first kind, ordinary discontinuity on the right. Because left hand limit coincide with the value. So, it is continuous from the left hand side, but it is not continuous from the right hand side. So, what we say is x naught is a point of discontinuity of our kind 1, but from the right hand side. So, it is ordinary discontinuous from the right hand side. Similarly, if suppose if limit of this function f x when x tends to x naught plus coincide with the functional value f x naught, while the left hand limit exists, but is different from the value of the function f x naught, then we say it is then x naught is said to be ordinary discontinuity on the left. Okay. So, that is, for example, let us consider the function f x equal to x within small bracket, where x within small bracket denotes the positive or negative axis of x over the nearest integer and when x is midway between the two when x is midway between two consecutive integers, then the value of this is 0. It means what? So, it means like, suppose we have the function, say here is n, here is n plus 1. Let us take these two consecutive integer. Then this point is n plus half. It is the middle point for this interval. If the x lies here, the value of this x will be denoted by x minus n. Okay. So, x minus n. if x lies here, then in that case the value will be denoted by x minus n plus 1. So, that is the x is defined as x minus n when x lies between n and n plus half. Okay. When x lies between n and n plus half, the nearest integer is n. So, in that case it will be subtracted from n, x, and we get x minus n. But when x lies between n plus half to n plus 1, then nearest integer will be n plus 1. So, in that case this will be defined by x minus n plus 1. So, that will be the difference for this. And when x is exactly equal to n plus half, then what happen? If x is exactly n plus half, the value of this is given to be 0. So, this is the graph. Okay. So, if we look the graph, what is that? Suppose I am taking the positive side. So, let us take the interval 0, half, 1, and then 3 by 2, then 2, 2, 5 by 2, like this, and so on. Now, between the interval 0 to half, between 0 to half, what is this? This curve will be like, if x lying between 0 and half, so here n is 0. So, it will be defined as x only, that is the curve will be something like this. Okay. But it does not contain this point, and as well as it does not contain this point, because x is lying between 0 and strictly 0 and 0. Okay. Now, take this, as soon as the point comes over here, what is this value? This is coming to be x minus 1, x minus 1. So, it is like this, when x minus 1 and x equal to half, the value will come out to be below. So, below minus 1, and when it is 1, then it is coming to be 0. So, basically this line will be by minus x. So, here between x minus the curve, the function f x, so hence we can say the graph of the function, the positive value of x, for positive values of x, for positive values of x, the graph, hence the graph of x will consist of the lines y is equal to x, in between 0 to 1, when in the over the interval 0 and half, then it will consist x minus 1 over the interval half to 1, and continuous like this, x minus 2 over the interval, say this interval is 3 by 2 half to 3 by 2, sorry, it will go like this because here it will start from this, and then it will go from here directly 1. So, it will go something like by minus x and then 3 by 2 something. Okay. So, we get this one, and then 3 by 2 to 5 by 2 like this, 3 by 2 to 5 by 2, and so on, continue this. So, this is the graph for this, and remember these endpoints are not available here. At the point integers point, the value is coming to be what? When it is integers, say n and n plus 1, and n and n, this value is again defined as say integers positive or negative, is it not? So, x minus x is integer, it becomes the 0 for that. Okay. So, that is what is going. Now, what we see here is, whenever the point is, suppose I take the point n to n plus 1. Okay. So, let us take this n, here is n plus 1 and here is n plus half. So, what will be the left hand limit of this function when x is n plus. So, the value of limit of this function f x when x tends to n plus half, this is the point from negative side. From the negative side when you say, then what will be this? The function will have the, when this side it will be x minus n type. So, we get the x minus n type, but x is n plus half. So, basically this is equal to equivalent to this is n plus half minus n. So, basically this is half. So, when you are taking the function, this function is this one, is it not? So, limit of this means x equal to x plus h. So, here you write x n plus half plus minus h. So, we can say this will be equal to that is, here we can write it, that x equal to n plus half minus h and then minus n and limit of this thing, is it not, when h tends to 0. So, basically it comes out to be half. So, when you are choosing the limit from the negative side, the value is coming to be plus 1. Then when you are taking limit of this function f x when x tends to n plus half positive side, then this will be equal to what? N plus half plus h minus next term will be n plus 1. This term will be subtracted and taking the limit h tends to 0. So, minus n will go and basically it will come out to be minus 1. So, right hand limit comes out to be minus 1, and what is the f of n plus half? It is exactly coming to be 0, because on the middle point we are taking already assuming to 0. So, function therefore, the function f x has ordinary discontinuity discontinuities for x equal to n plus half, where n is an integer. Similarly, for the negative side we can get for this. Okay. So, this is the point of ordinary discontinuity or discontinuity of the first kind. Let us take another example. Suppose I take, which is a very interesting and famous one, always we used a box function, where f x equal to box x, where box x we mean the denotes the greatest integer not greater than x, So, greatest integer not greater than x. So, let us see what is the graph of this. If you look the mod x graph, the graph of this function f x is this one. Now, when x lying between 0 and 1, the greatest x dash denote the greatest integer not greater than 1. So, what is the integer? Is only 0. It means the curve will be like this. Okay. It will start from the 0, but it will not touch 1. So, we have this gap. Now, from 1 to 2, when you take 1 to 2, then the greatest in x denotes the greatest integer, means the integer not exceeding by x. So, 1 is the integer. So, here we are getting the graph like this, start it here up to go this. Here again this point is missing. Then 3. So, when you got the 3, you get again this one, again this point is missing, where this is 3, and continue. Similarly, when you take minus 1, you are getting something like this, is it not, and so on, so forth. Okay. Like this. So, this is like a step function. It is a step function. Obviously, integral points are the point of discontinuities. So, the graph function, then we say So, what is the graph of the functions for the positive x consist segment of line? Okay. and the left hand limit and what not right. Now, clearly here when you take the limit of this function f x, when x tends to n is an integer say 0 n plus, then this value will be what? This is equal to n plus h and limit h tends to 0. Okay. But n plus h lies between n and n plus n. So, basically this is n, h tends to 0, is it not? Because the greatest integer is only n. So, limit of this when you take the n plus 0, it is n. The limit of this function from the left hand side, x tends to n minus, n is integer, let n be a positive integer. I am just taking any integer, but positive integer let us take, then we get for the negative one. Then the negative side, left hand limit of this is the right hand limit. So, left hand limit will be n minus h and limit h tends to 0, but n minus h is strictly less than n. So, it lies in the interval n minus 1 to n. So, this limit will come out to be n minus 1, is it not? And what is the f of n? F of n is 0, f of n, that is f of n will be what? Integer. So, it is n. So, f of n is. So, what we say, limit left hand limit exists, right hand limit exists, but they are not equal. They are not equal. So, every integral point, every integral point is the point of discontinuity of first kind. Okay. Now, here one more thing is, since the limit of f x when x tends to n plus is n, which coincide with the value of the function. So, it has a continuity in the right hand side, discontinuity in the left hand side. So, we say it is a discontinuity on the left. Therefore, f x has ordinary discontinuity on the left for all integral values for all integral values left for all integral values of x, but is continuous on the right at these points. So, this is the third type of the discontinuity will be, we call it as a discontinuity of second kind. Okay. Now, what is this discontinuity of the second kind? When the limit of this left hand limit, right hand limit both does not exist. That is, a function f x is said to have a discontinuity of second kind at a point x equal to x naught if the left hand limit and right hand limit if left hand limit or right hand limit both left hand or right hand limit both do not exist. Okay. They are definitely, and left hand limit do not exist, right hand limit do not exist. In fact, so neither left exists nor right exists. So, what happened that? For example, if we take the f x equal to say sin 1 by x. This we have seen already this function. What is the behavior of the function? If I look this function, here x, this is y, and just I am taking say here y is equal to 1, y is equal to say minus 1. Okay. Now, graph of this function, if you look the graph will be something like that. Say here something like this, is it not? And as soon as it comes here, it is very closed, very closed, and like this, but it never touches here. Okay. Similarly, here this is very closed. Okay, very closed for this, and something like this, something like this. So, only at this means around the point 0 it gets so much congested, and frequently it going up and down very fast. That is, x near to x equal to 0, it has a sudden jump. At this point it has value 1, immediately in the nearby point it has a value minus 1. So, it has a sudden jump near at the point x equal to 0, in the neighborhood of 0. So, let us see, we claim that this x equal to 0 is the point of discontinuity of second kind. Let us see, suppose I take positive side pehle. First you take x is greater than 0. Okay. Then if I take the number x equal to say 1 by 4 n plus 1 pi by 2. Okay. So, what happened this? Sine function we know, sine pi by 2 is 0. Then, because if we take the graph of the sine function, this is the graph of the sine function, sine 0 is 0, like this. So, sine 0 is 0, sine pi is 0, sine 2 pi is 0, sine 3 pi is 0, and so on. But sine pi by 2, this is the point pi by 2, where it has a positive value 1. Sine of this thing 2 pi plus 5 by 2, that is 5 pi by 2, it has a 1 value. Then again this 3 pi, 4 pi, so it is 9 pi by 4 pi plus pi, 9 by 2 pi. Then this value, the function has a value 1. So, when it is pi by 2, sine of 3 pi by 2, sine of 5 pi by 2, and so on, the value of this is is 1, and then if we look the sine 3 pi by 2, sine 3 pi by 2, this is our 3 pi by 2, this value 3 pi by 2, here it is 7, is it not? 7 pi by 2, so 3 pi by 2, sine 7 pi by 2, and so on, the value is coming to be minus 1. It means when the point x, so 1 by x is this, so x is very near, n is sufficiently large, the point is very close to 0. So, when it has the value n is the function, so this function f x has the value 1 when n is equal to what? N is 0, n is 1, n is say 2, and like this, and equal to minus 1 when n is what? N is here say 3 pi by 2. So, we are getting n is equal to say if I choose the function f x, if we take x is equal to 1 by 4 n minus 1 pi by 2, then the value of the function f x is minus 1 for n is equal to 1, n equal to 2, which 8 minus 7 pi by 2, and like this, continue. So, we have a sequence of the point approaching towards 0 where the function has a sudden jump +1 to -1 and like. Similarly, in the left hand side. So, this function we said the limit of this function f x, which is sin x when x tends to 0 minus, that is limit of this sin 1 by x when x tends to 0 minus does not exist. Similarly, limit of this function f x when x tends to 0 plus does not exist. 0 plus 0 minus here 0 plus does not exist. So, x equal to 0 is the point of discontinuity of second kind. So, this is what we have. There are some other also functions we can go at. Now, one more function we say that of course, this is not very important, but still we if one or the more function at alpha is infinitely great, if either left hand limit or right hand limit is indefinitely great, means very large, it goes to infinity when this left hand or right hand limit goes to infinity, then in that case the function f, then f x is said to have an infinite discontinuity at the point x equal to x naught. For example, suppose I take the function f x, which is 1 minus x minus say x naught, okay, and the value of this at the point x naught I am choosing to be 0. Now, what happens? If you take the limit of this function f x when x approaches to x naught from the negative side, then this is the same as 1 over x naught minus h minus x naught limit h tends to 0, is it not? Now, this is equal to what? This is nothing but tends to minus infinity, because this value will go to basically x naught cancel and h is sufficiently small. So, it goes to minus infinity, and when you go to the plus side f x when limit x tends to x naught plus side where x naught, then what happens is limit x naught plus h minus x naught and then h tends to 0. So, this will be tending to plus infinity. So, what is the left hand limit or right limit or any both of them, it goes to very large infinity, then point x equal to x naught is a point of discontinuity for this, okay, infinite discontinuity of this at x equal to 0. Okay. And then, so almost this we have covered. One is more examples which we can prove the results. Of course, without proof we can just say in the neighborhood of a point of discontinuity, in the neighborhood of the point of discontinuity of the second kind, the function makes an infinite number of oscillations. oscillations, because the reason is very simple. When you take the limit of the function either from the left hand side or right hand side, then you get a sequence approaching toward that function, where along a different sequence you have a different values. So, in fact, if x naught is the point of discontinuity of second kind, then we can get one sequence where the limit of the function will be say alpha 1, then another sequence will be obtained where the limit of the sequence is minus something, say alpha 2 or something. So, there is a sudden jump, makes an infinite number of oscillations. So, that is the case of this. Second is, of course, proof you can go through, that is very not difficult. The set of points, of removable discontinuities of a function is countable. Okay. The reason is, proof is very like this. Suppose that S, if the set S, suppose the set S, which is the function, set of those function x, where f x has removable discontinuity, Okay. Let S be this. Suppose S is not countable. Then it has a component. Say B, which is dense in itself. Okay, that will be a point alpha B is such that any is one side that. So, a point alpha we can find, a point alpha of the set B is such that in any, so a point alpha is such that in any neighborhood of alpha, on one side there are infinite number of points infinite number of points at which the functional values limits are all equal, but are different from functional value, at that point. Therefore, alpha is a point of discontinuity of second kind, which is a contradiction, because we have assumed the alpha as a point removable discontinuous point. Therefore, our assumption is wrong. So, the set S is countable. Similarly, another result is the set of points of ordinary discontinuity, that is discontinuity of the first kind, discontinuities of a function is countable. That is all. Thank you very much. Clear? So, proof is just based on this, and thank you very much.